Today we finally want to talk about what entropy is. I know we spent a few days laying all the groundwork, and I want to spend a moment to refresh your memory on some of those key ideas. So the first thing is, make sure you understand the difference between microscopic and macroscopic. So we looked at the any given Sunday activity, and we saw that for a 4-game season, there were 16 different microscopic ways with which the season could play out. We had one way was 4 straight wins, another was 4 straight losses, and then everything in between. Each of those 16 different microscopic options were equally probable. The results of all the games were 50-50, so each of these 16 were equally likely. The outcome of the season, macroscopically, would be the number of wins the team ended up with. So macroscopically, there were not 16 options, there were much less. So you could have 0 wins, 1 win, 2 wins, 3 wins, or 4 wins. 5 different macroscopic outcomes. At the end of the season, there were 5 different ways a team could end up. When we looked at them, the most likely macroscopic outcome was 2 and 2. There were 6 different microscopic ways that we could end up with that result. So that result is most likely, even though microscopically all the different ways the season could play out are equally likely. We saw the same thing when we looked at randomly having letters generate. If we generated 51 random letters, spaces, question marks, periods, semicolons, both of these strings of 15 characters were equally likely. However, macroscopically, having something make sense versus gibberish had a totally different macroscopic likelihood. It was incredibly unlikely to have these characters produce some sort of intelligent statement. However, it was extremely likely that you would just get gibberish. So microscopically, equally likely; macroscopically, incredibly unlikely. We tried to apply this to gases, which is our main thrust for what we're doing with this. We'll come back to this in a little bit. We applied it to cards. We saw that both 5 strings of cards are equally likely on a microscopic level. When we look macroscopically, this outcome gives us nothing. This outcome is a royal flush, and we get 250 times our original bet. So macroscopically, getting a royal flush is extremely rare, and getting nothing is extremely likely. However, microscopically, each string is equally likely. It's just there's a lot more ways of getting nothing than there is of getting the 250 for the royal flush. So again, we hope that you guys understood the difference between microscopic and macroscopic. When we look at a sample of gas, we measure the macroscopic properties, the volume, the pressure, the temperature. Microscopically, all kinds of things could be going on behind the scenes. Okay, I want to also make sure you understand the whole idea of when things are interchangeable and when they're not. Okay, so if you look at this deck of cards, or this hand that was dealt from a deck of cards, you might realize something unusual is happening, and you'll notice that there are 2 of some of these cards. And you might think somebody's cheating, but it turns out that's not true. It just so happens that this hand was dealt not from a standard deck of cards, but from a pinochle deck of cards. And the difference is, in a pinochle deck, all the cards are 9 or higher. So you won't ever find cards lower than 9. Instead, you'll see duplicates of some of the cards. And from the microscopic point of view, the important thing to realize is these cards are interchangeable. It doesn't matter that they're physically two different cards, they have the exact same properties. Okay, so that will be important later on. We can see the same idea on Words with Friends. So here I have 7 unique letters. I'm going to hit the swap button to move them around and see if I can see any words appear. Maybe a different arrangement will lead to a different word, something that actually I could use as a 7-letter word. Well, how many different ways can I arrange these letters? Well, it turns out there are 7 different letters I can put in the front, which means 6 and 5 and 4 and 3 and 2 and 1. And if you want to write this out using factorial, it would be about 7 factorial. This works out to about 5,000, even more than 5,000 different ways you could arrange these letters. Most of these arrangements are going to be gibberish, but a few of them will actually give us 7-letter words. Okay? So again, microscopically, all the different arrangements are equally likely. Macroscopically, it's more likely you're going to get gibberish than it is that you're going to get a 7-letter word that you can play. Okay, what I'd like you to realize again with this whole idea of things being interchangeable is that 7 factorial for the number of microscopic states, that's only true if every one of those things is unique. If, however, we have a situation like this, boy was this a bad hand, where I had 6 O's and only 1 C, all of these O's are interchangeable. So whether or not the O for this tile is here or here, and this one is here, they're identical. They're identical microscopic states. So it turns out there are only 7 different ways I can arrange these letters. The C could be in any one of these spots. And once the C is established in that spot, we know every other spot is an O. Okay? So when you have duplicates, it's going to lower the number of microscopic states. That's the important idea. Duplicates that are identical in every single way. They're interchangeable. It makes no difference which O we're talking about. They're just both O's. Are going to lower the number of possible microscopic states. Okay, so let's go back to our any given Sunday. We remember this was for a 16-game season. We saw that this is pretty likely, this is less likely. We have some that are extremely unlikely. And then we saw when we upped it from a 16-game season all the way to a 2,000-game season, what happened is we get a whole bunch of different macroscopic states that become pretty much impossible. And then a very narrow range of macroscopic states that are going to be extremely likely. What this means is if we start with our system in this spot and we randomly shuffle it, we're almost 100% guaranteed that we are going to move into that other position. If we started in this area and shuffled it, we're going to move to that center point. And if we start in the center and shuffle it, we're going to stay pretty much with the exact same condition that we had originally. Okay, so as we add more and more elements, the likelihood of something being in a certain spot becomes much stronger. The number of macroscopic states that won't happen grows really quickly. Okay, so now that we've learned all that, how does it apply to entropy? So this was a long journey, but hopefully it will give you a clear understanding of what we mean by entropy and how to calculate it. So it turns out that the first mathematical definition, at least the first one that survives, the one that we would still use today, came from Ludwig Boltzmann. You could see his years and you can see where he's from. And you can see this is his grave marker. And you'll notice in addition to having a bust of him, he also put on there his famous equation for entropy. So let's take a look at it. Okay, so again, this is what it looked like in his time. This is the way we're going to write it. All right? So S stands for entropy, this mysterious quantity. When we actually get a number associated with it, this is how it's going to come about. So S, entropy. This symbol, omega, again, he used W. We don't want to use that anymore because we now use that for work. But this omega stands for the number of possible microscopic states that can account for a given macroscopic condition. So for instance, if we wanted to look at 8-8 as the condition for our football season, this 12,870, that would go in as our omega. It is the number of microscopic ways that we can have a certain macroscopic outcome. Okay? You take that number, they're going to be huge numbers, so then we take the log of it to make it into a much smaller number. Okay, and then it turns out you multiply it by Boltzmann's constant, which we're not going to do quite yet because these are not actually a system of molecules. This is just a football thing just to give you something to latch on to. So I'm just going to do this first part or second part, and I'm going to take the log of all these numbers. You'll notice that when I take the log of 1, I get 0. That means anytime you have a macroscopic condition that only has one microscopic state, the entropy of that is 0. It is 100% predictable. There's only one way you could get that macroscopic outcome. You'll notice that as this number gets bigger, the log of the number also gets bigger, but nowhere near at the same rate as the original numbers did. So again, it takes a big range of numbers and turns them into a smaller range of numbers. Now you'll notice if we think about the graphs that we had, we are going to tend to move when we shuffle things and change things around into a macroscopic state that has the highest entropy. Things are naturally going to progress into a state of higher entropy. You guys may remember running across entropy in chemistry with your Gibbs free energy, and this will give you a little hint in terms of the units that we're going to use for entropy. You might also be able to deduce it from the fact that we're using Boltzmann's constant. In both cases, the units are going to be joules per Kelvin. So if we have Kelvin for the temperature and entropy is in joules per Kelvin, the Kelvins are going to cancel, and that will allow us to subtract these two quantities, which will both then be measured in joules to get us our Gibbs free energy, which is also measured in joules. Okay, so again, this is going to be high entropy, these are going to be really low entropy, and things are going to move toward a state with higher entropy. And that is the basis of the second law of thermodynamics. It says any isolated system will always progress toward a state of higher entropy. Okay, the entropy of an isolated system will never go down. It can either go up or it can remain constant, but it can't get more organized. That's not going to happen. Okay, oftentimes we'll hear entropy described as times arrow, because when you take a system, it's always going to move in a direction toward greater entropy. So when we see something like this, we know that we are watching that video backwards. We are not going to see a uniform solution separate back into the original unique locations for each of these different fruits, okay? Things are going to become more disordered rather than more ordered. However, when we look at something like this person on the pendulum and we watch him swing back and forth, we may not realize that we are watching this backwards. It looks exactly the same as if this video was playing forward, and the reason is there is no change in entropy as they swing back and forth. So watching it forward or backward is going to look identical because this is a completely reversible process. Okay, so when we talk about times arrow, that just means that when we see things becoming more disordered, when we see entropy increasing, that is really having us see the passage of time. Anyway, with all that in mind, what I'd like you to do today is work through this Google form to make sure that you understood all the basics for entropy.